So sometimes when we look at the picture for area, it makes more sense to use horizontal rectangles instead of vertical rectangles. And you can do that. We saw examples of that when we very first started looking at Riemann sums. So if you do that, then we want to integrate with respect to y. That allows us to go vertically up and down the axis as opposed to horizontally on the x. So sometimes you're going to have graphs that are already written as a function of y. That makes it easier. And sometimes it helps us to avoid having to break the function into smaller integrals. So there's really two different ways that you can approach finding the area between two curves. If you're going to go with respect to x, that's going to use vertical rectangles. And we saw those two examples in the previous video. Top curve minus bottom curve is the integral that you want to do. If you want to use horizontal rectangles, that is fine. We just need to make sure that we set it up so that we are integrating and our boundaries, our limits of integration need to be values on the y-axis, and you'll do the rightmost curve minus the leftmost curve. And this should be an equation that is all in terms of y if you're going to do it that way, okay? So let's look at why we might want to do that, for example. So this first one here, we want to find the area of the region bounded by the graph of x equals 3 minus y squared, and x is equal to y plus 1. Now, the first thing is that if you want to use your graphing calculator to graph this, you have to solve the equation for y, because you can only enter y equals into your graphing calculators. Now, if you do that, that's very easy. I could add y squared and subtract x, so I get y squared equals 3 minus x. Then when I take the square root, don't forget that we get plus or minus the square root of 3 minus x. The reason why that's so important is our graph is going to look like this. The positive square root of 3 minus x is going to look something like this. And the negative square root is going to look something like this. So what it really ends up graphing for us is a sideways parabola. If you don't have the plus or minus, you're not going to get both of those pieces. So you would have to put this in as two separate equations to your graphing calculator, one with the positive in front, one with the negative in front. And then if I want to graph x equals y plus 1, that would be the same as y equals x minus 1. So that is going to be a graph with a y-intercept of -1 and a slope of +1. So it's going to look like that. So the area that we want to find is going to be inside this region here. Okay, so that kind of weird little slice. Now, let's think first if we were going to do this with respect to x. The fact that these equations are solved for x and defined in terms of y is a good clue that we want to go horizontally. But here's the other reason. If you think about wanting to do vertical rectangles, here would be an example of a representative rectangle in this case. The top curve is easy to see is the line, and the bottom curve is the parabola. However, at this point here where they switch, that's no longer the case. The line is not actually part of this at all. And in fact, now it's the positive square root that is the top and the negative square root that is the bottom. So you would need two different integrals to be able to find this total area. However, if we just, let me see if I can get some of this stuff off of here, whoops, without losing too much of the picture. That'll have to be good enough. Okay, if we use a representative rectangle that is horizontal, then you can see that all up and down here, the parabola is going to be the rightmost curve, and the line is going to be the leftmost curve. So that is the way that we want to set this up. Now we can tell, again, by looking at this one, because I know that I plotted these 2 points specifically on both graphs, but to be absolutely sure, we want to set these two equations equal to each other to find our intersection points. So 3 minus y squared equals y plus 1. We get 0 equals y squared plus y minus 2. And that factors to y plus 2, y minus 1. So our two y values are -2 and +1. And that does appear to match what we had on our graph. So we know that we did that pretty much correct. So those are going to be our limits of integration. Our integral then is going to go from -2 to +1. And the rightmost curve is the parabola. Again, that's this sideways parabola in terms of y. So this is 3 minus y squared minus the line, which is y plus 1. And this integral is with respect to y. Do make sure, because I know we've got such a habit of writing dx, make sure that all your variables agree inside your integral, because you don't want to lose notation points there because of that. And so you can work out that integral. When we integrate, first you got to combine your like terms and all of that. You should eventually get, if you work this out on your own, well, let's combine this first. So we have -2 to 1 of, oops, hold on. Well, I just lost all of that writing. But when this simplifies down, you should have -2 to 1 of -y squared, here come the dogs, minus y plus 2 dy. And when you work that out, you should get 9/2. And so that's just an example of how you can work these with horizontal rectangles instead of just vertical. And sometimes this is going to make the problem a whole lot simpler. You can always choose to do one or the other, but typically one is going to be easier than the other. So that's just something to keep an eye out for.